If we possessed a time machine, where would we set our destination? Instead, it would be a voyage to the very first moment of existence, 13.8 billion years ago. What would we find at the end of this pilgrimage? This journey into the primordial past is not just a flight of fancy, it is a fundamental quest that has captivated the human spirit for millennia. The question of where everything came from is perhaps the most significant question we can possibly ask. Welcome to a special exploration where we embark on this very journey. Our mission is to delve deep into the heart of the Big Bang Theory. It is the story of our own genesis, tracing our lineage back to the dawn of space and time. The question of our cosmic origins is more than a scientific puzzle. It is a deeply human and philosophical inquiry. Where did all of this come from? Was there a beginning? These questions are woven into the very fabric of our consciousness. This desire for understanding has given rise to countless creation myths and philosophical systems. Contemplating the universe's origin forces us to grapple with concepts that stretch our minds. This is where science and philosophy intersect. What if the universe truly emerged from absolute nothingness? The transition from non-existence to existence is the ultimate miracle. Ultimately, the search for our cosmic origins is a search for meaning. From the simplest hydrogen atom to the intricate neural networks in our brains, it is the story of everything. For most of human history, our understanding of creation came from myth, not data. Ancient cultures developed cosmogonies to explain the world. These stories attempted to order a chaotic universe and answer questions of origin. Greek mythology began with chaos, a dark void. From this came Gaia, Tartarus, and Eros. This theme of a primordial state giving birth to reality is common. Hindu cosmology views creation as cyclical. The universe is born, destroyed, and reborn. Abrahamic traditions describe creation ex nihilo. In the beginning, God created the heavens and the earth. Ancient Chinese philosophy explains the cosmos through the Tao. From Wuji came yin and yang. These narratives reveal a human need to understand our existence. They provided explanations and a sense of purpose. Ancient myths gave way to observation as humanity sought to understand the universe through discoverable laws. Pioneers like Galileo replaced divine decree with natural law and systematic inquiry. The telescope unlocked cosmic secrets, revealing a universe of staggering scale. Galaxies were separated by unfathomable voids. The universe was far larger and more complex than imagined. Groundbreaking observations led to the Big Bang Theory. This theory became the most successful explanation for the origin and evolution of the cosmos. It's a story about understanding our place in the universe. We learn to read the cosmic story, written in the light of distant galaxies and the afterglow of creation. Ancient Greeks imagined the universe beginning not with order, but with chaos, a formless, boundless void holding all potential. From this abyss, primordial entities like Gaia, Earth, Tartarus, the underworld, and Eros, love, emerged, laying the foundation for everything that followed. Across cultures, similar myths of a primordial void, like Egypt's endless waters of Nu, reflect humanity's shared intuition. Before creation, there was a mysterious nothingness, a canvas for existence to unfold. Hindu cosmology envisions the universe as an endless cycle, creation, preservation, and dissolution, governed by Brahma, whose single day spans billions of years. Each cosmic day brings forth a new universe, followed by a night of dissolution, echoing the rhythm of eternal renewal. This cyclical vision, with its vast timescales and recurring universes, prefigures modern ideas like the Big Bounce, reminding us that cosmic origins can be imagined as a perpetual dance, not a single event. The Abrahamic religions introduced the radical idea of creation ex nihilo, God bringing the universe into existence from absolute nothingness as described in Genesis. In the beginning, God created the heavens and the earth. This concept shaped Western thought, establishing a universe with a definite beginning and a creator outside space and time, a perspective that still sparks dialogue between science and theology today. In Taoist philosophy, the universe unfolds naturally from the Tao, the nameless, formless source, through the interplay of yin and yang, whose balance gives rise to all things. Rather than a planned act or a cycle, this origin story sees the cosmos as a harmonious, organic process, emphasizing balance, unity, and the wisdom of following the natural flow. The cosmic egg appears in myths worldwide, symbolizing a unified origin where all potential is contained within a single enclosed form, echoing the scientific idea of a singularity. Whether in Hindu, Chinese, or other traditions, The eggs breaking marks the birth of the cosmos, a powerful metaphor for the transition from unity to the diverse world we know. Creation myths reveal a universal human impulse to understand our origins. Our ancestors used metaphor, story, and spiritual intuition to construct narratives about the universe. These frameworks provided answers to existential questions and encoded wisdom about reality. Ancient myths touch upon themes that resonate with modern cosmology. The human mind gravitates toward fundamental patterns when contemplating ultimate origins. The scientific revolution ushered in a new way of knowing based on empirical evidence and observation. This transition marked cosmology's migration into a quantitative science. Understanding ancient myths sets the stage for the scientific discoveries that followed. These stories are the foundation upon which our modern inquiries are built. For centuries, the concept of a static universe, championed by Isaac Newton, dominated our view of the cosmos. In this model, the stars and galaxies were fixed, suspended in an infinite space. However, paradoxes like Olber's paradox, "Why is the night sky dark?" hinted at flaws. In 1915, Einstein's general relativity predicted a dynamic universe either expanding or contracting. Einstein, clinging to the static model, introduced the cosmological constant, later calling it his biggest blunder. The universe, however, would soon reveal its dynamic nature through observations from the farthest reaches of space. In the early 20th century, a question divided astronomers: were spiral nebulae small clouds within our Milky Way, or immense distant island universes, entire galaxies like our own? This was the subject of the great debate between Shapley and Curtis. Henrietta Leavitt's discovery of the Cepheid variable star-period luminosity relationship provided a new cosmic yardstick. Finding Cepheids in spiral nebulae would reveal their distances and show if we were one of countless galaxies in a vast cosmic ocean. Edwin Hubble, working at Mount Wilson Observatory, had access to the most powerful telescope at the time. In 1923, he aimed it at the Andromeda Nebula, searching for Cepheid variable stars. Hubble's calculations revealed Andromeda was nearly 1,000,000 light-years away, an entire galaxy in its own right. The universe was not just one galaxy but billions. He also discovered redshift, indicating galaxies were moving away. Hubble's law showed the farther a galaxy, the faster it receded, proving the universe was expanding. The very fabric of space was stretching. Hubble's discovery shattered the static cosmos paradigm, suggesting the universe had a history. Imagine rewinding the cosmic movie. Space contracts, galaxies converge, and the universe becomes denser and hotter. All matter compresses into an infinitesimally small, hot point. Georges Lemaire proposed this super-dense state, calling it the primeval atom. This implied a finite age, a beginning, making the universe's origin a scientific question. Despite the compelling logic of Lemaire's primeval atom and the powerful evidence from Hubble's observations, the idea of a universe with a distinct beginning was not immediately accepted. In fact, for many decades, it remained a highly controversial and fringe theory. The scientific establishment was still deeply attached to the idea of a static, or at the very least, an eternal universe. The primary competing theory at the time was the steady-state model, championed by astronomers Fred Hoyle, Thomas Gold, and Hermann Bondi. This model accepted that the universe was expanding, but proposed that new matter was continuously being created in the voids left behind, ensuring the universe looked the same on average at all times. The steady-state theory was elegant and philosophically appealing to many scientists because it avoided the thorny issue of a singular beginning. It described a universe that was eternal, with no start and no end, which seemed more scientifically respectable than a theory that sounded uncomfortably like the creation stories found in ancient religious texts. The debate between the two models was fierce and often contentious. Proponents of the steady-state model were particularly critical of the primeval atom idea, which they considered unscientific and speculative. They demanded more direct evidence for such a cataclysmic origin event before they would abandon their more conservative, unchanging cosmic picture. The now famous name for the theory, the Big Bang, was actually coined by one of its fiercest critics, Fred Hoyle, during a BBC radio broadcast in 1949. Hoyle used the phrase derisively, intending to mock the idea of the entire universe exploding into existence from a single point, a concept he found absurd and simplistic. He meant for the name to sound ridiculous, to paint a picture of an unscientific, chaotic explosion that lacked the elegance of his own steady-state model. He hoped the catchy, dismissive term would highlight what he saw as the theory's biggest flaws, and prevent it from gaining wider acceptance in the scientific community. Ironically, the name stuck. Instead of discrediting the theory, the term Big Bang proved to be incredibly catchy and memorable, and it was eventually adopted by the theory's own proponents. While the name is somewhat misleading, the event was not an explosion in space but an expansion of space itself. It captured the public imagination and provided a simple, powerful label for a complex idea. The term that was born from ridicule ultimately became the banner under which the theory would march forward. The stage was now set for a new phase of discovery, one that would seek out the definitive evidence needed to prove that the Big Bang was not just a clever idea but the true story of our cosmic origins. The term Big Bang often conjures an image of a colossal explosion. However, cosmologists describe it as the expansion of space itself. This changes how we picture that first moment. There was no center. The expansion happened everywhere at once. Imagine the universe as the fabric of a balloon with dots representing galaxies. As we inflate it, every dot moves away from every other dot. The Big Bang was the rapid stretching of space-time. The distances between all points are increasing. The Big Bang happened everywhere. We are all living within the aftermath of that initial expansion. The Big Bang theory describes the origin of matter, energy, space, and time. According to Einstein, space and time are interwoven into space-time. This fabric is bent by mass and energy, causing the universe to expand from the Big Bang. Before this moment, space and time did not exist, leading to the question, what came before? The Big Bang wasn't an event in time, but the beginning of time itself. The universe was compressed into a singularity, an indescribable state. From this, expansion began, setting the cosmic clock in motion. If the Big Bang was the first moment, what caused it? The initial expansion is the ultimate uncaused event, the starting point of cosmic causation. The Big Bang was an expansion of space-time. Rewinding the cosmic clock, the universe becomes incredibly concentrated, driving temperature and density to extremes. In the first fractions of a second, it was a uniform inferno, hotter and denser than any star. No atoms existed, just a turbulent plasma. This quark-gluon plasma can only be recreated for fleeting moments in particle accelerators. All the matter and energy of our observable universe was compressed into a volume smaller than a grapefruit. The cosmic microwave background radiation, a faint afterglow, confirms this hot, dense beginning. The early universe was a brilliant, energetic furnace. Today we experience four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces appear distinct, but modern physics suggests they were unified in the early universe. The Big Bang theory predicts that in the extreme energy of the early universe, these forces behaved as a single superforce. As the universe expanded and cooled, it passed through phase transitions. At each transition, a fundamental force separated from the unified whole. Gravity was the first to emerge. Later, the strong force separated, triggering cosmic inflation. Finally, the electroweak force split into electromagnetism and the weak force. All four fundamental forces were established, setting the stage for the universe's structure. One of the most famous equations in all of science, Albert Einstein's E equals mc squared, holds the key to understanding how the universe became filled with matter. The equation reveals a fundamental equivalence between energy and mass, linked by the square of the speed of light, a very, very large number. This means that a tremendous amount of energy can be converted into a small amount of mass, and vice versa. In the extreme, high-energy environment of the early universe, this process was happening constantly. The primordial fireball was so energetic that pairs of matter and antimatter particles were continuously being created from pure energy, only to collide and annihilate each other, turning back into energy in a flash of light. This process, known as pair production, created a vibrant, chaotic soup of particles and their antimatter counterparts. For every electron created, a positron, an anti-electron, was also formed. For every quark, an anti-quark. The early universe was a perfectly balanced maelstrom of creation and annihilation, where matter and antimatter were locked in a cosmic dance. If this perfect symmetry had been maintained, the consequences would have been dire for our own existence. As the universe expanded and cooled, all the matter and antimatter would have eventually found each other and annihilated completely, leaving behind a universe filled with nothing but photons, a sea of light with no substance. Our universe would have been beautiful, but sterile and empty. Fortunately for us, for reasons that are still not perfectly understood, this symmetry was not perfect. A tiny imbalance, a slight preference for matter over antimatter, must have existed. For roughly every billion pairs of antimatter particles, there were 1,000,001 particles of matter. This subtle asymmetry, known as baryogenesis, is one of the most profound mysteries in cosmology. We do not yet know the exact mechanism that caused this imbalance, but its effect was monumental. After all the annihilations were complete, that tiny 1 in a billion surplus of matter was left over. This small remnant, this cosmic leftover, formed everything we see around us today. Every proton, every neutron, every atom in every star, planet, and living being is a survivor of that great annihilation. We are made of the matter that was lucky enough to not find an antimatter partner in the chaotic first moments of the universe. The vast sea of photons that resulted from all the annihilation events became the cosmic microwave background radiation, the very afterglow that provides evidence for this hot, dense past. Einstein's equation, therefore, is not just an abstract formula, it's the recipe for our own existence, explaining how the pure energy of the Big Bang was transformed into the tangible, physical substance of the cosmos. For its first 380,000 years, the universe was a hot, dense, opaque fog of free-roaming atomic nuclei and unattached electrons. Light was trapped. The universe was a featureless, incandescent plasma, expanding and cooling. Reaching an age of about 380,000 years, the universe cooled enough for electrons to be captured by atomic nuclei, forming the first atoms. In a cosmic instant, the universe went from opaque to transparent. This ancient light is what we observe today as the cosmic microwave background, the baby picture of the universe. Our journey into the cosmos begins at the very edge of our understanding, in a period so brief and extreme it defies all current physical theories. This is the Planck era. During this epoch, the entire observable universe was compressed into a region smaller than a single proton. The conditions were so extreme that the very concepts of space and time begin to break down. To describe this state, we would need a complete theory of quantum gravity. Without it, the Planck era remains a mysterious, impenetrable wall. As the universe expanded, gravity separated and became the distinct force that we experience today. This marked the end of the Planck era and the beginning of a new cosmic epoch. Following the Planck era, the universe experienced rapid growth. Known as cosmic inflation, the universe expanded at hyper-accelerated rates. The size of the universe increased by a factor of at least 10 to the 26th. This solves some of the biggest puzzles of the standard Big Bang model, like the horizon problem. Inflation proposes the entire observable universe originated from a tiny, causally connected patch. Inflation explains the flatness problem by stretching any initial curvature to an enormous degree. Tiny quantum fluctuations were stretched to astronomical scales, becoming the seeds of all future structure. These formed the first stars, galaxies, and the vast cosmic web we see today. After the breathtaking expansion of inflation, the universe continued to expand, but at a much more moderate pace. The enormous energy that had driven inflation was converted into a flood of elementary particles, heating the universe to an incredible temperature of over 1 trillion degrees. This marked the beginning of an era where the universe was filled with a hot, dense, and turbulent soup of matter and energy known as the quark-gluon plasma. For the next few microseconds, this was the state of all matter in the cosmos. There were no protons, no neutrons, and certainly no atoms. Instead, there were only the most fundamental building blocks of matter, roaming free in a sea of energy. The primary residents of this primordial soup were quarks, the particles that would later combine to form protons and neutrons, and gluons, the particles that carry the strong nuclear force and glue quarks together. In the extreme heat and density of this era, quarks and gluons were not confined within larger particles as they are today. They moved about freely, constantly colliding, and being created and annihilated in pairs. The universe was a perfect, seething fluid of these fundamental constituents, a state of matter so extreme that it can only be recreated on Earth for fleeting moments inside the most powerful particle accelerators, like the Large Hadron Collider at CERN. This era was also a battleground between matter and its shadowy twin, antimatter. According to our theories, energy should convert into equal amounts of matter and antimatter. For every quark, an antiquark should have been created. These particle-antiparticle pairs would then collide and annihilate each other, turning back into pure energy. If this symmetry had been perfect, the universe would have cooled into a sterile sea of light with no matter left over to form stars or planets. But for reasons we still don't fully understand, a tiny imbalance occurred. For every billion antiquarks, there were about 1,000,000,001 quarks. This slight asymmetry was the secret to our existence. As the universe expanded and cooled to a few trillion degrees, it reached a critical threshold. The strong nuclear force became powerful enough to trap the free-roaming quarks and gluons. In a cosmic phase transition, the quarks were confined together in groups of 3 to form the first stable protons and neutrons, the building blocks of atomic nuclei. After all the matter-antimatter annihilation was complete, that tiny surplus of matter remained. Every atom in your body, every star in the sky, is made from the leftovers of that primordial battle. The universe had successfully passed through its most chaotic phase, and had now created the stable ingredients for the next stage of cosmic evolution. As the universe sped past its first second of existence, it had cooled enough for protons and neutrons to form, but it was still too hot for them to bind together into stable atomic nuclei. Any nucleus that happened to form would be instantly blasted apart by a high-energy photon. For the first few minutes, the cosmos was a sea of individual protons and neutrons, along with electrons and photons. But as the clock ticked towards the 3-minute mark, the temperature dropped to about 1,000,000,000 degrees Kelvin. This was the perfect temperature for the next crucial step in creation, the era of Big Bang nucleosynthesis. It was a brief but pivotal window of opportunity for the universe to forge the first chemical elements. During this period, which lasted from about 3 to 20 minutes after the Big Bang, protons and neutrons began to collide and stick together, bound by the powerful strong nuclear force. The process began with the fusion of a proton and a neutron to form deuterium, an isotope of hydrogen. Once deuterium was formed, it could quickly capture another proton or neutron to create heavier nuclei. The primary products of this cosmic forge were helium-4, which consists of 2 protons and 2 neutrons, along with trace amounts of lithium and beryllium. By the end of this period, the primordial soup of the universe had been transformed into a mixture of about 75% hydrogen nuclei and 25% helium nuclei by mass. This process could not continue indefinitely. After about 20 minutes, the universe had expanded and cooled to a point where the density and temperature were too low to support further nuclear fusion. The cosmic furnace was shut off. This is why the Big Bang primarily produced only the lightest elements. Heavier elements like carbon, oxygen, and iron that are essential for life were not created in this initial event. They would have to wait billions of years to be forged in the fiery cores of stars and dispersed through supernova explosions. The Big Bang set the initial chemical stage, providing the raw fuel that would power the stars for eons to come. The predictions of Big Bang nucleosynthesis are one of the strongest pillars of evidence for the entire theory. Our calculations of the conditions in the early universe lead to very specific predictions about the primordial abundances of these light elements. When astronomers measure the composition of the oldest, most pristine gas clouds in the distant universe, they find that the ratios of hydrogen, helium, and lithium match these predictions with stunning accuracy. This remarkable agreement between theory and observation gives us great confidence that we understand the story correctly. It is a powerful confirmation that the universe did indeed pass through this hot, dense phase just a few minutes after it began. For the next 380,000 years, the universe continued to expand and cool, but it remained a dark and foggy place. Although the first atomic nuclei had formed, the universe was still hot enough that electrons were not bound to them. Instead, they zipped around freely in a hot, dense plasma. This sea of free-roaming electrons made the universe completely opaque. Photons, the particles of light, could not travel far before they scattered off an electron, being absorbed and re-emitted in a random direction. It was like living inside an incredibly thick, glowing cloud. Light was trapped, unable to stream freely across space. An observer inside this cosmic fog would have seen a uniform, blindingly bright glare in every direction. During this long, dark age, the seeds of structure that were planted during inflation began to grow. The slight variations in density meant that gravity was starting to pull matter from less dense regions towards more dense ones. The plasma wasn't perfectly smooth, it was full of vast, slow-moving pressure waves, like sound waves sloshing through the cosmic fluid. These are known as baryon acoustic oscillations. As gravity pulled matter in, the intense radiation pressure from the trapped photons pushed it back out, setting up a cosmic rhythm. These oscillations left a subtle but detectable imprint on the distribution of matter, a characteristic pattern that we can still observe in the arrangement of galaxies today. A critical turning point was reached when the universe reached the age of 380,000 years. By this time, the temperature had dropped to a cool 3,000 Kelvin, about the temperature of the surface of a red dwarf star. At this cool temperature, the free electrons no longer had enough energy to resist the electromagnetic pull of the atomic nuclei. They were finally captured, combining with the hydrogen and helium nuclei to form the first stable, electrically neutral atoms. This event is known as recombination. With the electrons now locked into atoms, the primary obstacle for photons vanished almost instantaneously. The cosmic fog cleared. In a single, dramatic moment, the universe went from being opaque to transparent. The light that had been trapped scattering inside the plasma was now set free to travel across the cosmos unimpeded. This flood of ancient light, released 13.8 billion years ago, has been traveling through the expanding universe ever since. Today, we detect it as the cosmic microwave background, or CMB, a faint cold afterglow of the Big Bang that permeates all of space. When we create maps of the CMB, we are not just looking at old light. We are looking at a direct photograph of the infant universe at the very moment it became transparent. It is the ultimate baby picture of our cosmos. The most compelling evidence for the Big Bang is the cosmic microwave background, or CMB. It's the residual heat from creation, the afterglow of the early universe. This was confirmed in 1965. Two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon the first direct evidence of the Big Bang's afterglow. Subsequent missions have mapped this radiation with precision. These maps revealed minuscule temperature fluctuations in the CMB. These were the primordial seeds of structure. It's a detailed blueprint of the infant cosmos, a snapshot that aligns with the story of the Big Bang. The Big Bang theory is supported by the observation that our universe is expanding. Edwin Hubble discovered this in the 1920s, studying light from distant galaxies. He noticed redshift, a shift towards the red end of the spectrum. Hubble's law showed that the farther a galaxy, the faster it recedes. This indicates the expansion of space itself. This expansion supports the Big Bang model. Telescopes confirm Hubble's law across vast distances. Redshift measurements allow us to calculate the universe's age. This evidence supports the Big Bang origin. Beyond the cosmic microwave background and the expanding universe, the Big Bang theory predicts the chemical composition of the early cosmos. According to the model, the intense heat created a nuclear furnace, forging light elements like hydrogen and helium. Astronomers test this by observing ancient objects like quasars, analyzing light to measure element abundances in early gas clouds. The results are a stunning success, matching predictions with accuracy and providing strong evidence for the early hot phase of the universe. Further evidence comes from galaxy distribution. Galaxies aren't randomly scattered, they form a cosmic web. Simulations accurately reproduce this structure, giving us confidence in the Big Bang model. The Big Bang theory successfully describes the universe, but what came before? According to the standard model, the question is meaningless if time began with the Big Bang. Some physicists speculate our Big Bang was a transitional phase in a larger cosmic history. One idea is the Big Bounce, from the collapse of a previous universe. Another possibility is our universe emerged from a larger multiverse. Pushing beyond the Big Bang requires a new chapter in physics, a theory of quantum gravity. Developing this theory is the primary goal for a generation of physicists. The Big Bang model reveals that familiar matter accounts for only a tiny fraction of the cosmos. Observations reveal galaxies spinning so fast they should fly apart. Cosmologists suggest dark matter, an invisible substance, to solve this. Its presence is inferred through gravitational influence. Dark matter outweighs normal matter 5 to 1, forming a cosmic web. The universe's expansion is accelerating, leading to the concept of dark energy. Dark energy, an intrinsic property of space, acts as anti-gravity. It makes up 70% of the universe, yet its nature is unknown. 95% of the universe is composed of these dark components. Understanding this dark side is the next frontier, requiring new ideas to reshape our understanding. The fine-tuning problem highlights a startling coincidence. The fundamental constants of nature appear exquisitely balanced. One explanation is the multiverse hypothesis, suggesting our universe is one of countless others, each with different physical laws. Though these universes are unobservable, scientists seek indirect evidence. The fine-tuning problem forces us to confront deep philosophical questions: cosmic design, statistical inevitability, or an undiscovered physical principle. Understanding this cosmic coincidence drives theoretical physics, pushing us to explore the very foundations of reality. The Big Bang leads to a profound question: how will it all end? The universe's fate is tied to the battle between gravity and cosmic expansion, driven by dark energy. Cosmologists considered two possibilities: the Big Crunch or the Big Freeze. The Big Freeze, or heat death, involves eternal expansion, pushing galaxies apart. Stars will die, leaving black holes. Black holes will evaporate. The universe will become a cold, dark void. A more violent end is the Big Rip. If dark energy grows stronger, it could tear apart galaxies, stars, and even atoms. Discovering our ultimate fate is a key goal of cosmology. We began with a simple question: what would we see if we traveled back to the very first moment of the universe? Our quest has taken us from ancient myths to the vibrant cosmos revealed by modern science. This journey is more than just a history of science, it's the human spirit's quest for knowledge. It is the greatest story ever told, the story of everything that is, was, and ever will be. The tale of the Big Bang tells us how a universe of unimaginable heat could blossom into the complexity we see. Stardust organized itself into conscious beings capable of looking back at the universe and piecing together their origin story. To know that the iron in our blood was forged in the hearts of long-dead stars is to feel a deep connection to the cosmos. It gives our wonder a foundation, grounding our sense of awe in a reality that is even more spectacular than our ancestors could have ever imagined. The story is vast, but its message is simple: we live in an evolving, dynamic, and deeply interconnected universe. Our exploration of cosmic origins reveals a powerful, unifying thread that runs through all of human history. The fundamental questions we ask today are the same questions our ancestors asked as they huddled around fires, gazing at the canopy of stars above. Where did this all come from? How did it begin? What is our place in the grand scheme of things? From the philosophers of ancient Greece to the astronomers at Mission Control today, this shared curiosity binds us together across cultures and across time. It is a defining characteristic of our species. The quest to understand the universe is not just a scientific endeavor, it is a deeply human one. The answers we have formulated have changed dramatically over the millennia. We have moved from creation myths that gave us a sense of purpose and place, to a scientific cosmology that gives us a sense of scale and physical connection. Yet, the underlying motivation remains the same: a desire to make sense of our existence. In the past, we saw ourselves at the center of a divinely crafted world. Today, science places us on a small, rocky planet orbiting an average star, in an ordinary galaxy among billions. But this shift in perspective is not a demotion. It is an invitation to see ourselves as part of something immeasurably vast and magnificent, a part of the universe that has woken up. This journey has taught us that every answer we find seems to unlock a dozen new, more profound questions. The discovery of the expanding universe led us to the Big Bang. The Big Bang led us to questions about cosmic inflation, the nature of the singularity, and what came before. The confirmation of the theory's predictions revealed a cosmos dominated by mysterious dark matter and dark energy, substances that make up 95% of the universe but whose nature remains completely unknown. Our cosmic map is filled with vast continents of knowledge, but they are surrounded by even vaster oceans of ignorance. And that is a wonderful thing, for it means the adventure is far from over. The story of the universe is ultimately our story. We are not separate from it. We are a product of it. The laws of physics that guided the expansion from the first second are the same laws that operate within our own bodies. The atoms forged in the Big Bang and in the cores of stars are the very atoms that form our brains, enabling us to ponder these cosmic mysteries. This realization fosters a profound sense of belonging. We are not merely observers of the cosmic pageant, we are participants. We are the universe's way of knowing itself. Our quest for knowledge is the cosmos becoming self-aware. The universe may have begun with a bang 13.8 billion years ago, but the expansion of human curiosity will never cease. Our journey to understand our origins is an ongoing process, a story that is still being written. With each new telescope, Each new particle accelerator and each new theoretical insight, we add another sentence to this grand narrative. We are living in a golden age of cosmology where the mysteries of the dark universe, the possibility of a multiverse, and the ultimate fate of the cosmos are being actively investigated. The next discovery could be just around the corner, ready to once again revolutionize our picture of reality. The quest is not just for scientists, it is for everyone who has ever looked up at the night sky and felt a sense of wonder. The great questions of cosmology, of beginnings and endings, of our place in the vastness, are questions that belong to all of humanity. They inspire our art, our philosophy, and our collective imagination. They challenge us to think beyond our everyday concerns and to contemplate our existence on the grandest possible scale. Engaging with this story connects us not only to the universe but to the long chain of thinkers and dreamers who came before us and asked these same questions. As we stand on the precipice of new discoveries, we are reminded that our current understanding, as successful as it is likely incomplete. The Big Bang Theory is the best description we have of our cosmic history, but it is not the final word. Future generations will look back on our science just as we look back on the science of the past, and they will see the gaps and the flawed assumptions. They will build on our foundations armed with new technologies and new ideas, pushing the frontiers of knowledge ever further into the unknown. The quest is infinite. Our journey ends where it began, with a sense of awe and a spirit of inquiry. From the chaos of myth to the light of science, our relentless drive to understand the cosmos is perhaps the noblest of all human endeavors. It is a journey that takes us to the edge of time, to the dawn of existence, and ultimately, back to ourselves. The universe began with a moment of brilliant, explosive creation, but the true engine of discovery is the quiet, persistent, and unending expansion of human curiosity. The story is not over. The next chapter is waiting to be